Hello everyone, in this video I'm going to be talking about solution process, and along with that I'm going to be talking about the explanation of like dissolves like and how to know whether something is able to dissolve in something else. So first thing I'm going to talk about is the solution process. So basically, solution process is like, what the heck does that even mean? It's basically just the process of a solute dissolving into a solvent. So what we're saying there is something dissolving, and how that works and the energy involved in that. So some key definitions is solute and solvent, and then also solution. So a solute is a chemical that is being dissolved. So for instance, salt or NaCl. And then the solvent is what is being, or what is dissolving the solute. So the solvent is the thing that is going to be breaking apart the molecules of the solute in order to create a solution. So I have a little picture here kind of like depicting that. So your solute is the thing that you're adding, so like your salt. It can also be a liquid, so it can be something like ethanol, which is an alcohol. And then your solvent, which is usually a little bit stronger, and that's kind of how, well, it doesn't always have to be stronger, but I don't know, for some reason I remember solvent because it's the thing that's breaking things, and solvent has a V in it, which is a big letter to use in a Wordle. I don't even play Wordle. What is no, not Wordle. Scrabble, I think. I don't even play Scrabble. I don't play any of those word games. But it's a bigger word, it has a V in it. So to me it's stronger. The thing that's going to be breaking the intermolecular forces, which we'll talk about in a second. But that's how I remember it. If you're having trouble remembering that, I know, very odd of me, but that's how I do it. So anyway, back to the pictures. So we have our solute going in, and our solvent is the blue thing, which I guess you could say is like water here. And then you kind of like mix those together. You can see there's a little bit smaller pieces, so they're slowly starting to dissolve. The bonds are slowly being broken, but then once everything is completely dissolved, you get your solution. Most of the time there's no weird color change. I just did the color change because it shows it a little bit better so you can see what's happening. So when you're breaking those intermolecular forces, usually that requires energy. So we say it's an endothermic reaction, right? So, that's usually if you have like a pot of water and you add salt to it, the salt's going to sit at the bottom of it if you add a lot of it, and it's not going to mix in until you stir it. One second, I'll just close my door. So it's not going to dissolve until you mix it. And what mixing actually does is it not only is spreading the salt through the water, and the water is able to, hit the molecules more, but you're also putting in some kinetic energy. So you're adding energy to that, which helps it dissolve. And then the next thing is the formation of a solution. That is usually what is that called? Exothermic. Sorry, that's so bad. It's usually exothermic. So the formation of a solution usually will end up releasing heat. Usually it's not a lot of heat. Sometimes it will, sometimes it needs heat to do it, but most of the time we say that it's an exothermic process. So taking a look, like a little bit of a closer look of how to determine if a solution process is endothermic or exothermic as a whole. As I said before, we know that the breaking of the intermolecular forces is a endothermic reaction. So within a molecule, within multiple different molecules, let's say we have NaCl, the Cl is going to be slightly negative, this is going to be slightly positive, and then that's going to attract the NaCl of another one, and that's actually how salt becomes like a cube, is because of like, wow, that was actually a decent cube for how quickly I drew that. The reason why it's able to become a cube and become a solid is because these forces are so strong that they're basically like attracting each other and almost working as one molecule, but they're not strong enough to be one molecule, and they're not sharing their electrons the way that they would. They're simply just attracting each other. But in order to break, let me go back. In order to break this bond here, it's not actually a bond, it's an intermolecular force, or this attraction. it requires energy to pull these guys apart, right? And that makes sense, right? We talked about that before when we had even just a molecule. Let's say that we had H2O. That bond cause energy, and things like that. So the next thing is forming the solution is going to release energy, as we said before. And that makes sense, right? So let's say that this and our water molecule, these two are going to attract each other. Now, that's going to release energy. We know that back from when we were doing, what is that called? Entropies and things like that. We know that breaking the bond requires energy and making a bond releases energy. So you get exothermic. So in general, we say that the delta H of something that's mixed, which would be like the solution plus like these two coming together, we say that if that's greater than both of the energies required to break the intermolecular forces between a solvent and a solute, then that's going to be exothermic, which this equation makes a little bit more sense to me when we say that when you add them together, the delta H of the solution, that will, whether that's positive or negative, that will tell you it's exothermic or endothermic, but the reverse is the same thing for endo, where if you add the solute or the solvent and the solute together and those delta H's are greater than the delta H of the mixture, then that's going to be endothermic. But we'll do a practice problem on that because this is like a little bit confusing, I'm sure, the way that I'm explaining it. But if you use this equation, it helps out a lot. The fact that if you add all of the delta H's to make the entire solution that's breaking the bonds and making the bonds, then the delta H will tell you whether it's exo or endo. So let's do a practice with that. So this says it requires 20 kilojoules to dissolve the NaCl in water. Okay, so the delta H of the NaCl is 20 kilojoules. And the water requires, so delta H of the water requires 5 kilojoules to undergo this process. The resulting, so delta H of the mixture, the resulting solution releases 30 kilojoules of energy. Is this process endo or exothermic? Okay, so it's actually going to be negative because it's releasing it, so that's going to be at negative 30 kilojoules. So we're going to add them all together. So we have 20 kilojoules plus 5 kilojoules plus a negative 30 kilojoules. And I'm sure most of you guys can do that in your head, but it's always good to do it on your calculator. 25 plus 5, oh, not 25, 20 plus 5 minus 30, that is going to give us negative 5 kilojoules. And because it's negative, we know that it's going to be exothermic. So we could say this is exothermic. Okay. And that would mean that the solution is exothermic. So if you were actually holding this solution, 5 kilojoules is quite a lot, actually. This is not like a normal amount of energy. I just did that because, just for practice. If you were holding something that released 5 kilojoules of heat, you would feel that. You would feel the heat being released, and it would be hot. Versus if this was something that was endothermic, that required energy, it would feel cold because it's absorbing the energy from the surroundings, right? That's a really great concept to get down, is the fact that if something's exothermic, you'll feel it. If it's endothermic, it'll feel cold. But yeah. Okay, so that's it for that. Now let's talk about how do things dissolve each other, right? So why does salt dissolve in water? And why does salt not dissolve in something that's nonpolar? So we always use the saying, like dissolves like. That's the easiest and the most plain way to say it. Two things that have similar polarities are going to dissolve within each other. So basically what this means is that a solvent will dissolve a solid with similar polarity. So if we look at an example of ethanol and water, I'll just draw those out for you guys. So we have H2O, which has hydrogen bonding. I'll put hydrogen bonding, just write it like that. And then ethanol, let's draw that out. So you don't know what ethanol is, you'll actually learn that when you take Gen Chem 2, and then you'll further learn more about ethanol when you take organic chemistry, if you were to take organic chemistry, but I'll just draw that out. So it looks like this, CH CH3OH. Actually, this is a CH2, sorry. CH2OH, yeah. So that's ethanol. So that's what makes vodka, right? And this is another hydrogen bond. So these two things can dissolve each other, right? So the ethanol is going to get dissolved in the water, and the water is like they're going to be miscible, and you can mix them together, right? And then when we look at CH4 and Cl4, we know what CH4 looks like. If we do our Lewis structure, it's going to look like that, which is nonpolar. And we have our Cl, Cl, Cl. These are all even, so this is also nonpolar. So these two can also dissolve in each other, right? So whichever one's stronger will dissolve the other one usually. So let's say that this one's a little bit stronger because of London dispersion forces. It weighs a little bit more. The Cl4 will dissolve the CH4 because of their similar polarities. So let's take a look at a quick practice problem. So this question asks which dissolves in H2O and which will dissolve in this molecule here, which is actually, I'll just write this here, 1, 2, 3, 4, meth, eth, pro, but. This is actually butane. You don't need to know that, but just to put a name to the picture. Yeah. So, which one will dissolve in H2O? So I'm just going to write a little note down here that this has hydrogen bonding. So let's look for something that has hydrogen bonding or something that has, what's it called? Something that's ionic, right? So an ionic compound or something with hydrogen bonding. So the first one is actually nonpolar. This should be a 4 anyways, I don't know. That should be 4. So this is actually nonpolar, so we can say no, that won't dissolve in water. KCl, so K is usually is a metal, and this is a non-metal, so these two are going to be ionic, so we can circle that, so that will dissolve in the water. And then CF4 is also nonpolar, so we can say no. CH3OH, that's methanol. This is going to be having hydrogen bonding, so this will also dissolve in the water. Okay, now which one will dissolve in our butane here? So I'm going to say this is nonpolar. So let's take a look and see what here is nonpolar. The first one is ionic, right? We know that this is going to form a positive and this is going to form a negative when it dissolves, so that's no. We just did this one, positive and negative. Those are ionic, so no. This one, a little bit tougher to see. Let's draw it out, see if it's nonpolar. Okay, so once I drew it out, I realized, okay, the chlorine is actually going to be pulling in those electrons from everything else around it, so it's a bit stronger, meaning that it's going to be polar, so I'm going to write that. So this is going to be polar, so I'm going to say no, and then this one, draw it out. You don't have to draw it out. If you can recognize that it's polar versus non-polar, then that's fine. But drawing it out, we can see that all of these guys have the same polar bonds to them, so it's going to be even, so that will be our non-polar molecule. So that's all that I have for this video. I hope that this helps, and thank you all for watching.